Okay, and I started recording, so that's all set. Just get situated here. Okay. So last class, well, first of all, there's a couple of things I want to tell you. Those graded assignments, so GA5. And GA6. I actually posted the solutions to these. So I know one person emailed me and asked me to do that, and I finally got around to it. I kind of tried to delay in case anybody was handing them in, but nobody, everyone stopped. So anyway, those are up there now, and maybe they'll help you out with the exam. Because I know that GA6 is a problem very similar to it on the exam. So anyway, I just wanted to say that. And the other announcement I had was, please, if you're not seniors who are graduating or who know they are or aren't, who are graduating, let me know. Maybe that's a better way of putting it. So if you are graduating, then you let me know so I can file your grade early. Okay. So last class, I talked a lot about salts, at least at the end of class. So salts. First of all, what is a salt? Anybody have an answer to that for me? Let's see if I can get the chat back here. What the heck happened to it? Oh, there it is. All right, so what's a salt? All right, come on, get yourselves together and tell me, what is a salt? Somebody must know. That's right. It's an ionic compound that's formed in an acid-base neutralization reaction. Thank you. But another way to think about them is simply that they are ionic compounds. I could say any ionic compound with certain exceptions. So any ionic compound except hydroxides. Obviously, hydroxides wouldn't be made in an acid-base neutralization because they're bases, and oxides wouldn't either. They're not even soluble, so I don't even know why we bother considering them. So a salt is basically an ionic compound. And I talked last time about how salts can be acidic, basic, or they can be neutral. And I talked about how to figure out if a salt is acidic, basic, or neutral. And there's just a few bullet points here. If the anion, that's the negatively charged ion, is the conjugate base of a weak acid, then it is basic. And it will contribute towards making that salt basic, okay? If the cation, and for example, those there would be like acetate, fluoride, NO2 minus. Let me actually do a little more here. So acetate, for example, is the conjugate base of acetic acid. Okay, fluoride is the conjugate base of HF, and this is a weak acid. Why can't I put chloride on this list? Why isn't chloride basic? It is the conjugate. What is chloride the conjugate base of? HCl, yes. And conjugate bases of strong acids are not basic, they are neutral. That's because the stronger the acid, the weaker the conjugate base. HCl and other strong acids are so strong that their conjugate bases are so weak that they're not bases at all. So fluoride is a conjugate base of HF. ClO minus is the conjugate base of HClO, which is a weak acid. How do you know it's a weak acid? You look on the chart. All right. NO2 minus is the conjugate base of HNO2, which is a weak acid. Notice I do not have NO3 minus on this list because, again, it is the conjugate base of strong acids. Okay. So other anions like chloride, NO3 minus, bromide, these are conjugate bases of strong acids and are neutral. Okay, so another bullet point has to do with the cation. If the cation of the salt, we're still talking about salts, if the cation is the conjugate acid of a weak base, then it is acidic. Okay, so for example, NH4 plus, this is the conjugate acid of the weak base ammonia. So it is acidic. Methylamines, protonated form, CH3, NH3 plus is the conjugate acid of the weak base methylamine, and it is acidic. Other cations, the cations that pair, so those that pair with hydroxide in strong bases, like for example, sodium, calcium, these are neutral. And so I would say the metal ions in the first two groups. And that's all I've taught you about. I'm not going to give you some other, other metal ions that are not in those groups. They have a bit of a more complicated situation. So, we could tell by looking at a salt, we could look at the salt, we could identify its ions, and we'll be able to tell based on these criteria whether the salt is acidic or basic or neutral. But what I want to do is tell you, and I did this, I'm just going to do this briefly because I did it really last time, that there are some complications to this. And the one I'd like to talk about is, what if a salt has one acidic ion, that would be the cation, and one basic ion, which would be the anion. Then what? Okay, so here's an example. This is from activity 10B. There's actually 3 examples there that are done out. I'm just going to go over one of them, which is NH4 NO2, ammonium nitrite. It's not nitrate, it's nitrite. Okay, so if you think about these ions, you have the ammonium ion and the nitrite ion. And ammonium is the conjugate acid of ammonia, which is a weak base. And so that makes ammonium acidic. However, NO2 minus is the conjugate base of the weak acid, HNO2, nitrous acid. It's on the chart. So it is basic. So we have one acidic ion and one basic ion. So how do we figure out if this salt is acidic, basic, or neutral? So what you would do in these cases is you would find the Kb for this basic ion. And you'll also find the Ka for the acidic ion. And remember last time I showed you that you're not going to necessarily find these values on a table of acid or base dissociation constants. Instead, you have to calculate these from the Ka or Kb of the corresponding acid or base and Kw. So Ka here for NH4 plus is actually Kw over Kb for ammonia. So in general, Ka for the conjugate acid of a weak base is Kw over Kb for that base. So these things have to be conjugate acid-base pairs, okay? And also Kb for NO2 minus is Kw over Ka for the corresponding weak acid. So more generally, Kb for the conjugate base is Kw over Ka for the corresponding acid. Okay, so this is in general here, and these have to be pairs, conjugate acid-base pairs. So taking this down here, Ka for NH4 plus is 1 times 10 to the negative 14th over. Now, if I look up Kb for ammonia on the chart, it's 1.75 times 10 to the negative 5th. Interestingly, it's exactly the same value as Ka for acetic acid, but that doesn't matter to us here. So this Ka for ammonium is 5.7 times 10 to the negative 10th. It's not a very impressively large, it's actually quite small Ka, okay, but it is still, it's still meaningful. And over here, the Kb for NO2 minus is Kw over Ka for HNO2, which if you just go to the acid dissociation chart and look that up, HNO2, where it's right here, it's 4.5 times 10 to the negative 4th. Which is 2.2 times 10 to the negative 11th. Okay, so even though these are both very small numbers, this one is larger. So the Ka for NH4 plus is greater than the Kb for NO2 minus. And so as a consequence, ammonium nitrite is acidic. Okay, not very acidic because this isn't a huge, you know, anyway, these aren't like massive numbers, but it would be acidic. All right, so that's how you figure out whether these salts that are combinations of acidic and basic ions, that's how you figure out whether they're acidic or basic. But there would be no way, no easy way, certainly, for me to figure out what the pH of this ammonium, you know, if I made a certain molarity of ammonium nitrite, I couldn't figure out the pH of that solution. When we can figure out the pH of a salt solution is only when there is only one ion that is acidic or basic. If we have two, then, you know, that's not general chemistry. Okay, so the question is, you know, how how do we find out, how do we figure out the pH of a salt solution when only, and can only do this when the salt has only one acidic or basic ion, not both. Okay, so I'll show you a couple of examples, one for a basic salt and one for an acidic salt. And so here's a problem. What is the pH of a 0.1 molar solution of calcium nitrite? Okay, and notice that this calcium nitrite that there are actually 2 moles of NO2 minus per 1 formula unit of CaNO2. So that's going to be something we have to figure out. But how you solve a problem like this is you say, okay, the ions here, we have calcium, we have NO2 minus. This is neutral, so we don't have to worry about it. This one is the conjugate base of the weak acid HNO2, which I talked about just now. So it is basic. So this salt is basic. And you should keep that in mind, because when we finish this problem, you should get a pH that's greater than 7. And if you don't, you did something wrong. Okay, so we know that this is going to come out greater than 7 somehow. So now, what do I do with this? How do I figure out the concentration of basically OH minus, and then I could use that to figure out H3O plus at equilibrium. So I write what I've been referring to as the hydrolysis reaction, which is really just like the base dissociation reaction of any base. You take that base, you add water. This accepts a proton from water. It's a base. You get HNO2 plus OH minus. So this is exactly what you would do if you had the weak base ammonia and you were trying to figure out what the pH of that solution was. The only difference here is that when you set up your ice problem, you have to realize that you have twice the molarity for NO2 minus as what you had for the calcium nitrate, because you have that 2 there in the formula. Okay, so we basically have 2 moles of NO2 minus per mole of CaNO2 2. So instead of 0.1 molar, that's what you had for the calcium nitrite, this is 0.2 molar NO2 minus. And so when you do your ice problem, you have to be sure to put that in here, that this is 0.2 molar, not 0.1 molar. Again, we have water being the liquid, zeros for start, minus X, X, X. I hope that this is becoming somewhat rote for you at this point, that, setting up this type of ice problem. Okay, so we end up with, our KB for NO2 minus, which is the KB for this reaction. It's the K equilibrium for this reaction, is X squared over 0.200 minus X. And now, this is where this problem is slightly different from when you do a regular base equilibrium problem, base dissociation. And that is when you look at the chart, of course, this is not there, okay? You need to get KB for this ion from KW and Ka for HNO2. Did I just do this one? I think I did. I did. So if we go back and look here, I'm just going to use this exact same method here again. So the Kb of NO2 minus is Kw over the Ka for HNO2. I hope I get the same number. It'd be really embarrassing if I didn't, but yeah, I will. That's 1 times 10 to the negative 14th over 4.5 times 10 to the negative 4th, or 2.2 times 10 to the negative 11. It's not a very impressive, it's a pretty small value of K, but still it's going to make the solution a little bit basic. So then we have, I'll just take that. That's what this number is. Okay. And so now x squared over 0.2 minus x equals 2.2 times 10 to the negative 10th. So if this was a regular acid or base dissociation problem, not a salt, what would I have? What would I do next? What's the next step? Because it's the same next step here. What are you going to ask yourself?
The negative log?
Oh, not yet. We have to solve x first.
You cross multiply.
Well, before you do that, what about this thing here?
Oh yeah, someone just said it.
Yeah, so what was it? Can I do what?
Ignore x.
Yes. Okay, so we have the criterion. And the criterion is the initial concentration is 0.200 greater than 100 times 2.2 times 10 to the negative 10th. Well, that's 2.2 times 10 to the negative 8th. Well, that's 1, 2, 3, 4, 5, 6, 7, 2, 2. So is it greater? You bet it is. So yes, we can neglect the x. So that's exactly what we're going to do. X squared over 0.2 minus x equals 2.2 times 10 to the negative 10th. We're going to cross out the x. So we have a much easier equation to solve, right? We have x squared equals, now we do that cross multiply. Okay, and so x is simply the square root of this. This is actually 4.4 times 10 to the negative 12th. Which is 2.1 times 10 to the negative 6th. Now, can I just take the negative log here? You have to ask yourself, what is x? Go back. Let's go back. So in this problem, because it's a basic ion, X is the hydroxide. So if I take the negative log of this, what is that? What is that called? Is that the pH? It's the POH. That's right. So the negative log of that number is 5.68. So don't give me the answer 5.68. That's not the answer to this problem. That's the POH, right? That's not the right number, right? The pH should be a little greater than 7, not a little less than 7. So the pH is simply 14 minus 5.68. Keep the right number of sig figs, same number you had here. So that's 8.32. So that is the pH of this solution. Okay, so there's a couple of little things you have to do in this problem that you didn't have to do in a regular acid dissociation problem or base dissociation problem. First of all, you have to figure out what the K is. All right. And you have to do that by using the KW. Okay, that's one thing you have to do. The other thing you have to do is you have to, you know, you may get the POH at the end, and that's not what you want. You want the pH, so be careful. So just because I'm going to show you another example of what about if the salt is acidic? So let's consider one more salt. And this one, it has a much more complicated formula. But what you should do is take out the ion that you know, and you know the chloride ion well. Okay, if you take away a Cl minus, then you're left with the rest of this with a plus. Okay, and this is neutral. And what you should hone in on here is this nitrogen, because that's the clue that's going to tell you that this is the conjugate acid of a weak base in the ammonia family, I'm going to call it. Remember, I told you ammonia is like a prototype of a weak base. So as soon as you see that, you should be able to tell what's going on. This is just like NH4 plus. Did I do this? Yeah. There's two substituents that are methyl groups, and there's two hydrogens instead of there being four hydrogens. So anyway, so that tells you that this is acidic because it is the conjugate acid of a weak base. So if it was NH4 plus, that's the prototype, and it combined with water, it's acting as an acid, so it's a proton donor. It'll end up with the corresponding weak base, right? These are acid-base pairs, conjugate acid base. And the other product is going to be, well, a proton is transferred to water, so it's H3O plus. But this is not NH4 plus, but it's a sister to NH4 plus. So when you write this reaction, you will simply lose one of these hydrogens. And you'll end up with this equation. So listen, it's a little bit tougher, but use the prototype, okay? Now, once you have this equilibrium, again, we have to solve an ice problem, but I didn't give you a molarity. Okay, so let me write it here. What is the pH of a 0.50 molar solution of CH3 2 NH2Cl? That's what I'm solving here. So you should recognize this nitrogen in here as very significant. And you should look at how many things are bonded to nitrogen. You'll see there are 2 here and 2 here. That's 4. So that's very much like ammonium. Okay, so it's in that same class. So it shouldn't give you too much pause. All right, so now you'll have to set up an ice problem with the initial concentration here being 0.50 molar. This is a liquid. 0, X, minus X. So, you know, this part should be very familiar. So once again, we have, well, we have the Ka, now we have the Ka for this crazy thing. Yeah, is Kw over the Kb for the corresponding weak base. Oops, NH. which if I gave you this problem on a test, I'd have to make sure this was on the chart. This happens not to be on the chart because I have so few on the chart. I wanted to use something different, but that's okay because I know what the number is. And the number is 1 point, hold on, I'll write it down. 5.4 times 10 to the negative fourth. So this comes out to 1.85 times 10 to the minus 11. So that is the first complication. Well, second. The first one is you have to write this equilibrium. And maybe maybe that's a little unfamiliar to you. But the second thing is that you're going to need the Ka for this equilibrium. And to do that, you're going to have to find it from the Kb for the corresponding weak base. So this is Kb for the corresponding weak base. Okay. So now that I have that, I can set up my equilibrium equation to solve for X. And I have to ask myself the question, can I neglect the X? Is 0.5, it's pretty obvious. This is 10 to the negative 11th. This is 0.5. So the answer is yes. Okay. So I'm going to neglect the X. And then it proceeds just like the previous problem. X squared times 1 equals 0.50 times that K. Okay. So X is the square root of that. Which is 3 times 10 to the negative 6th. Now in the last problem, we ended up with an X that was the hydroxide concentration. But that's not the case in this problem. In this problem, X is the H3O plus concentration. So I can immediately take the negative log of this number, and that's the negative log of the H3O plus concentration. And that's going to give me, it's going to give me the pH, she said, finishing her thought. Okay, whatever. And so this comes out to 5.52. So it's slightly, it's acidic, but weakly so. Okay, because it's not that different. Yeah, it's acidic. It's not a strong acid, but it's acidic. So that's all I have to say about salts, you know, and actually in the packet, don't forget I have that handout on salts. And then I actually walk you through solving a problem. Okay. And then there are two activities. There's activity 12 and 13. And one of them is a basic salt. One of them is an acidic salt. And I'll give you these as special problems. And I'll give you a while to do them because I know that you have an exam. So like, how about like a week from Wednesday or something like that? So when is that? Today is the 12th, 14, the 21st. And I'm sure somebody will remind me to put up a thing there. These are extra credit problems. All right, so that's what I have to say about salts. Done with that. And now we have a very important section of the course, actually, or I should say a very important section of the acid-base unit, because it's very important in biology. And I know a lot of you are biology majors. And so that's this next topic, which is buffer solutions, is like very important in biology. And it has to do with these solutions that are special, and we refer to them as buffer solutions, and they are special. They're very special because they resist changes in pH when strong acid or strong base is added to them. Okay. And in fact, this is the topic for lab. So either tomorrow or Thursday, you'll be studying this in lab. Okay. So I'm just gonna to give you a bit of an example. I can't change my color. Why? That kind of thing drives me crazy, but oh well, we're stuck with red. So here's the example. I don't know why. All right, so suppose I have a beaker, and let's say that I have 90 milliliters of distilled water. Okay. And I measure the pH. And I get 7. You know, from lab last week, you know that you don't always get what you think you're going to get. But let's say we get 7. Okay, we'll do more of that pH measurement this week as well. And now what I'm going to do, and I wish I could do it in a different color, but I can't, is I'm going to add 10 milliliters of 1 molar hydrochloric acid to this beaker. Okay, so basically I'm adding 10 milliliters of 1 molar HCl, and the total volume is going to be 100 milliliters at the end, because it's going to be this 90 plus this 10. Okay, so if I want to figure out what is the pH, how do I figure that out? Hold on a minute. Okay, so how do I figure out what is the pH? So what I need to do is I need to do a dilution problem. I'm going to use this formula. Well, not that formula, because that's wrong. MdVd is McVc. So, you know, what I'm doing here is I'm taking 10 milliliters of a strong acid solution. I'm adding it to 90 milliliters of water. So I'm essentially making a dilution. The molarity of the diluted solution, so what I'm actually after is the concentration of HCl directly, in other words, right after adding the HCl. What is the concentration once I mix it up before it's dissociated, even though that's ridiculous because it immediately dissociates. But I'm going to use this equation, and I'm going to show you, we've done this before, but what the heck. So I'll take the molarity of my concentrated solution, which is 1 molar, times the volume I used, which is 10 milliliters, and divide it by the total volume, that's the 100. And this comes out to 0.1 0.10 molar, 10th molar. Okay, so I've just made a 0.10 molar solution of HCl. What is the pH of that solution? Well, all the HCl dissociates. 0.1 molar HCl gives me 0.1 molar H plus, right? So, because it's a strong acid. So the pH is the negative log of that 0.10, which is 1.00. 1 times 10 to the negative 1 is how you would write it in scientific notation. And the negative of that exponent is simply 1. So basically, what happened here is I had a solution with a pH of 7. I added HCl to make a 0.1 molar solution, and I ended up with a pH of 1. So the pH went from 7 to 1 with the addition of this relatively small amount of concentrated HCl. This is typical of what happens when you add a strong acid to pure water. It changes the pH. This is a drastic change in the pH. Why do I say so drastic? Because you don't forget that 1 pH unit is a factor of 10 in H plus concentration or H3O plus concentration. So in doing this, I started out at the beginning with my pH of 7 with 1 times 10 to the negative 7th molar of H3O plus. And it went up to 1 times 10 to the minus 1 molar of H3O plus. It changed by 6 orders of magnitude, a factor of 1,000,000 in H3O plus, just by adding that bit of strong acid. So there is, that's what I mean by a drastic change. Okay, now, if instead, so if I had added that same amount to 90 milliliters of a buffer solution, depending on the buffer and how I prepared it, what I can expect is that the pH of the distilled water, which is of course still 7, but then when I add the acid, maybe it would be 6.80 or 6.90 or 6.95 or 6 point whatever, 87. It'll change a little, and the amount it changes, the specific amount, so specific result depends on the composition of the buffer. So if I add acid to a buffer solution, I'm going to get a much, much smaller change in pH. So this is a pretty typical result. And I'm going to go over some calculations like this with you today, so you will be able to agree with me. Okay. So, all right, what is in the buffer that allows it to do this? What is it about the composition of the buffer that allows this to happen? That allows it to do such a good job resisting changes in pH. And buffers will do just as well with a base. If you add base, it will also stop the pH from changing. That's kind of really crazy about them, but it's true. All right, so what is it that's in the buffer? And what it is, a buffer solution has two components, each of which are very important. It has a weak acid and its conjugate base. Okay, so wait a minute. What if I made a solution of a weak acid? So I'm just going to say, wait a minute. Won't a weak acid solution have both of these? So this is kind of an aside. Supposing I have an HOAC solution. That's acetic acid, right? I know that I'm going to have this equilibrium in there. So doesn't that mean that I'm going to have some of this and some of this? So wouldn't that make all weak acid solutions buffer solutions? I mean, the answer is no to that question. So I guess what I'm asking is, does a weak acid solution have significant amounts of both of these? What's in that solution? What's in the soup? You know, if I make up a solution and it's HOAC, what's in there? Well, give me one thing that's in there. Nobody knows the answer to that? Sorry?
There's a hydrogen.
Give me something obvious. Yeah, there's some hydrogen. There's some H3O plus in there. But is there a lot? What's in there? What makes it a weak acid? Why am I calling it weak? What does that mean? How would I draw these arrows to reflect the actual concentration of the products and the reactants? Would these arrows be about equal in size? I don't have an X yet.
It's going to favor the reactants.
Yeah, it's going to be like this. Okay. So if I have a HOAC solution, it has a lot of this in it. It has very little of these guys in it. So this is not a buffer solution because it does not have an appreciable amount of acetate in it. It only has a very appreciable amount of acetic acid. So this, which is a solution of just a weak acid, does not contain an appreciable amount of conjugate base, OAC minus. It only has very little. So a solution of just a weak acid is not a buffer solution. So it kind of brings me to my next question. How do you make a solution that has both? How would you prepare a solution that has both an appreciable amount of acetic acid and an appreciable amount of acetate? What would you take off the shelf to do that? Okay. And this is what's done in lab. And I'm really sad that you don't get to make this buffer because frankly, making buffers is very important in all biology labs and chemistry labs, most of them anyway. So how you would do it is you would take a volumetric flask like this, okay? And acetic acid is a liquid, and you would pipette some drops of acetic acid in here. Okay, so you'd add some acetic acid in there. And then you would have to look on the shelf for some sodium acetate. And that's a solid. So I guess I could illustrate this as here. Here it's kind of like the liquid on the bottom, which will be the HOAC. And then you'll add some solid, right? NaOAC, and you'll fill it to the mark with water and mix it up. And that's how you have an appreciable amount of acetic acid. It's from the acid that you added and from the salt of that, that contains the conjugate base of that acid. Okay, so that's how you would make a buffer. It has the acid plus the salt, a salt where the anion is the conjugate base of that acid. So for example, HOAC and sodium acetate. Okay, so this is a salt containing acetate. Okay, so what are these magic buffer solutions that, you know, resist changes in pH and that work in the body? So what are the buffers in the body? Does anybody actually know? Because you guys study biology. Anybody know what buffers there are in the body? Well, I'm not going to say too much about them, but I'll tell you what they are. In blood, we have something called the carbonate buffer. And the weak acid is carbonic acid. And what is the conjugate base of H2CO3? What is the conjugate base? What happens if you take away an H plus? What are you left with?
HCO3
What's the charge on that?
minus.
Yep, that's right. That's bicarbonate. So these two are in blood, and it constitutes a carbonate buffer. Okay. In cells, there's a different one. It's called a phosphate buffer. And phosphoric acid is a relatively strong weak acid, but it's what we call a triprotic acid. And if you take away an H plus from it, you end up with H2PO4 minus. This is also an acid. So the weak acid in the phosphate buffer is H2PO4 minus. It's not H3OPO4. That would actually be too acidic for the pH that's needed in blood. Now, if you take away another H plus, you end up with this, and that is the conjugate base in this buffer, HPO4 2 minus. So these, this is called dihydrogen phosphate because it's got two hydrogens here, and this is called hydrogen phosphate. And this is the weak acid, this is the conjugate base, and that's what constitutes the buffer in cells. Okay, so what I want to do is, I don't want to use These are a little bit complicated because this is a diprotic acid, has 2 H's, and I'll use that next. But for my first example, I'd like to use a simple buffer. And the one I'm going to pick is one that has HNO2, nitrous acid, and nitrite ion. So this is a weak acid, and this is its conjugate base. Okay. So if I have a solution of both of these, so it's therefore a buffer solution, and I have HNO2 and I have NO2 minus, both in this solution. So it's a buffer. And I add, so now suppose I add strong acid. So I add HCl. The question is, what is this buffer going to do that's going to resist the change in the pH? So let's ask a really basic question. When you're adding HCl, okay, it's just like adding H3O plus, right? Because you know it's going to instantly dissociate. So it's like adding H3O plus, or even you could call it H plus. It's the same thing. Because that HCl is immediately going to give up its protons to water. It's going to dissociate, however you want to view it. So my question is, here's the question. Which part of the buffer, which component or part, which component of the buffer, in other words, HNO2 or NO2 minus, will added H3O plus react with? Will it react with the HNO2 or will it react with the NO2 minus? Okay, so it's going to react with something. Which is it going to react with? Remember, this is an acid. So what do acids react with?
Bases?
That's right. Which of these is a base? It's not a trick question. Which is an acid? It's the one with the H, right? It's the weak acid, HNO2. That's the acid. So this is the base. It's its conjugate base. So H3O plus, which is will react with the base, which is NO2 minus. And when it does that, what will it form? Well, H3O plus is just it's like as strong an acid as you can get. It's going to donate protons to NO2 minus. It's going to end up as water, and NO2 minus is going to become HNO2. So here's a very important and significant thing that happens in solution when you have a buffer. I guess I could look at it this way. You had a whole bunch of H3O plus in that solution from the added acid. However, it reacts with NO2 minus. So instead of having H3O plus in there, now we basically have water and HNO2. It's like you've taken the H3O plus and the NO2 minus has sucked it out of the solution to form weak acid. So you started with H3O plus, which is about as strong an acid as you can get, right? It really lowers the pH having H3O plus there. And it takes that H3O plus, the NO2 gets rid of it, kind of sucks it out, and this is what you end up with. It's like you're replacing a strong acid with a weak acid. So I'm going to say that the NO2 minus, I'm going to say sucks out all the H3O plus and replaces it with the weak acid HNO2. Well, how does a strong acid affect the pH? H3O plus. You take the negative log of whatever H3O plus is there, that's your pH. HNO2 is a weak acid, so it's only going to produce a little bit of H3O plus, right? Because it's weak. So because this is weak, it only produces a little H plus or H3O plus. So this arrow is basically a one-way arrow because this is a strong acid. So it basically takes out that H3O plus, replaces it with HNO2, and so the pH does not change nearly as much. Okay, that's basically what happens when you add an acid to a buffer. What about, and this is the really cool thing, what if you add strong base? And what's really cool is that a buffer can lessen changes to pH by adding strong acid, but it could also do the same thing when strong base is added. Okay, so when you add strong base, so if you add hydroxide, basically, so here you have your buffer solution with HNO2 and NO2 minus, and now you're adding hydroxide. What is that hydroxide going to react with? Is it going to react with the acid or is it going to react with the base in the buffer? Hydroxide is a base. It's going to react with the acid, exactly, HNO2. And then it's going to accept a proton and it's going to yield water. Plus, what's the other product here going to be? If you take away an H plus from this, you end up with NO2 minus. Don't forget the charge. The charge is important. Okay, so here what we have is that the HNO2 sort of sucked out the hydroxide and replaced it with a weak base. So this is a strong base. And here's a weak base. So we had a strong base that's going to raise the pH, but we suck it out, taken out, and replaced with a weak base. So the pH does not go up as much as if we had added it to water. So a buffer, why is it called a buffer? It's because changes to the pH are decreased. Another word you could use is mitigated or buffered. All these kind of go together. Okay, so a buffer solution in a buffer, to finish this sentence, changes in pH are decreased, mitigated, buffered, lessened, made smaller. So that's a buffer. So there's a couple of different things to learn about buffers, okay? There's basically two main types of buffer solution calculations that you have to learn how to do, okay? So there's two main types of problems. So the first is to figure out how to calculate the pH of a buffer solution. In other words, just the buffer, just the weak acid and the conjugate base, you know, based on the amounts of each that are added, or the molarities of the acid and the molarity of the base. So the first is how to calculate the pH of a buffer. And the second one is to how to calculate the pH when strong acid, a small amount of strong acid or strong base is added to that buffer. Okay. So suppose I have a solution. So I'm going to do an example. All right. I'm going to use, for my example, I'm going to use the carbonate buffer. All right. So suppose I have a solution that is 0.5 molar carbonic acid. So I add carbonic acid to a beaker. And I also add some sodium bicarbonate. Okay, so I add, and I end up with 0.4 molar HCO3 minus. So remember, this is the weak acid, and this is the conjugate base. And I just want to point out that we also sometimes call this just simply the acid, and sometimes we just call this the anion, right? Because if you take away an H plus here, the anion is HCO3 minus. Okay, so that's what we call it sometimes, but you have to realize that's the conjugate base of the weak acid. So it's, all right. So the first thing is, what is the pH of this solution? Now we know how to figure this out. We figured this out in other examples. In fact, we did an example of this in lab just last week, when we had acetic acid and acetate in the same solution. So here I have my carbonic. I start by writing the acid, dissociation, equilibrium. Okay, that's what I start by doing. So plus water. I get the donation of a proton to water, which leaves me with HCO3 minus bicarbonate ion, and of course, H3O plus. Okay, because it is an acid, carbonic acid. All right, if I want to figure out the pH, how would I do it? It's an ice problem. I know what these initial concentrations are. This is 0.5 molar. This is 0.4 molar. This is a liquid. This is 0. And then what do I put here and here?
Plus X.
Yep. And what about here?
Minus X.
Right. So I have my Ka for H2CO3, which I can look it up, and it's 4.3 times 10 to the negative 7th equals X squared. Oh, sorry, not X squared. 0.4 plus X times X over 0.5 minus X. Ooh, that doesn't look too friendly, right? This equation here. That's what I have to solve for X. But wait, can I neglect the X? Okay. So if we didn't have this 0.4 molar here, so if this only had 0.5 molar H2CO3, could I neglect X? Could I neglect the X in that situation? Well, is 0.5 greater than 100 times 4.3 times 10 to the negative 7th, which is 4.3 times 10 to the negative 5th. Is 0.5 greater than that? Yes. So I can neglect the X if there were no HCO3 minus. So my question is does adding HCO3 minus, what does that do to this equilibrium? Suppose I had a 0.5 molar solution of H2CO3 at equilibrium, and I add HCO3 minus, I add solid sodium bicarbonate until the molarity is 0.4 molar of the bicarbonate. That disturbs the equilibrium, right? Which way will the equilibrium go? Well, which way will it go? I disturb an equilibrium by adding product. Which way will the reaction go? Right, it'll go towards the reactants. It'll go in reverse. So what does this do to X? Is X going to get bigger or smaller if I drive the equilibrium this way? It's going to get smaller, right? Because X is the products, right? So what it does to X is makes it smaller. So if I could neglect the X in the problem when I only had 0.5 molar H2CO3, I can certainly neglect X here. This is the common ion effect, which we actually studied in lab last week. And we did that. We added acetate to a solution of acetic acid, and we saw that the pH went way up, which means the amount of H3O plus went down, which means we can neglect the X even more so. So here's my conclusion, and this is really the only thing you need to know. In buffer problems, because you have added conjugate acid, so because of the added conjugate acid, the X may always be neglected. Okay, so you don't even need to justify it. No justification is needed. Okay, so let's go back to the problem that we had. H2CO3 plus H2O goes to HCO3 minus plus H3O plus. I'm just recopying this now. We had 0.5, 0.4. Then we had minus X. 0.4 plus X. So we have Ka equals 0.4 plus X times X over 0.5. Oh, I'm going to take a rest. You can copy that. And the Ka was 4.3 times 10 to the negative 7. So we're going to neglect the X. That means we're going to cross it out here and cross it out there because it is small compared to these initial concentrations. And I know it's very small because I added a whole bunch of acetate in this problem, which drives the equilibrium more to that side. And so I can neglect my x. And then this becomes a relatively simple problem to solve. 0.4x over 0.5 equals the Ka. So if I cross multiply, I get 4.3 times 10 to the negative 7th times 0.5 equals 0.4x. So if I solve for x, wow, I'm way ahead of my notes. If I solve for x, I get that it's 4.3 times 10 to the negative 7th times 0.5 divided by 0.4. And when you do that, you get that when you plug these values in, you get 5.38 times 10 to the negative 7th. So that is the concentration of H3O plus. I kept an extra sig fig because I don't want to get round off error. And so the pH is the negative log of that. And it comes out to 6.27. Okay? But there's an even easier way. There's an easy way to solve this. And I'm going to show you, what that is. So we have this very nice equation here that where I solved for x. But what I'm going to do is I'm going to write in what each of the numbers here represents. So x represents the concentration of H3O plus. This 0.4 is the initial concentration. So if my acid is HA and my conjugate base is A minus, that's the conjugate base, or as I said, we call it the anion. Okay. In this case, it's H2CO3 and HCO3 minus. But speaking more generally, this would be the conjugation, the concentration of the conjugate base, the initial concentration. This means initial. This is the Ka, and this is the concentration of the acid initially. So for any of these problems with buffer, whether you have a conjugate, where you have an acid and its conjugate base, it turns out that the H3O plus concentration can always be found this way. It is the Ka multiplied by the initial acid concentration divided by the anion or conjugate base concentration. And you notice that this is just the Ka expression rearranged. But what we do is we have a log version of this equation, which is used all over the place in all biology labs and chemistry labs. The log version of this equation is always used for buffers, just about always. So if I take the log of both sides here, so I have a log of the H3O plus concentration. That's the log of this giant thing, Ka, initial acid concentration, over the base, conjugate base, or anion concentration. And then, if you remember, we have this formula, the log of AB over C. Well, when you have a product, you add the logs of each. When you have a quotient, you subtract. So I'm going to use this to simplify my equation here. So this is going to become log of H3O plus equals the log of the first thing here, which is Ka, plus, because this is times, the log of the HA concentration initially. And this is in the denominator, so that's minus the log of the anion concentration. And now what I'm going to do is I'm going to put a negative sign. I'm going to multiply by -1. So I'll put a negative here, a negative here, a negative here, and this negative is going to become a positive. And now I'm just going to recopy. Negative log of H3O plus equals the negative log of the Ka minus the log of the initial acid concentration plus the log of the A minus concentration initial. And now I'm going to make it look simple because what is the negative log of the H3O plus concentration? Anybody? What is that? By definition, that is what? It's a pH. And now we define this thing. Remember, I told you a while back that this P, we use it in science a lot. It means negative log. So the pKa is simply the negative log of the Ka. So this is the pKa. And now I have the log of A minus 0 minus the log of HA0. So I'm going to divide. I'm going to have log of A minus 0 over HA0. So I have this really concise, sort of simpler equation form. So I don't have to do an ice problem anymore. I don't have to set that up with X and minus X and all of that. I can use this equation. And in fact, if I do, so let's do this. Let's find the pKa. So our acid is H2CO3. The Ka is 4.3 times 10 to the negative 7th. If you take the negative log of that, okay, it should be about 7 because that's what the exponent is -7. So that turns out to be 6.367. I'm only entitled to 2 sig figs, but I always keep an extra one and round later. So this is the pKa. So I have pH equals 6.367 plus the log. Now, my A minus concentration was 0.4. My HA was 0.5. Notice the numerator is smaller than the denominator. That means that this here is less than 1. So the log of a number less than 1 is negative. If that number were greater than 1, then the log of that number would be positive. But in this case, when you take the log of that ratio, it comes out to negative 0.0969. So we have 6.367, just 2 sig figs after the decimal. If you add these together, you get 6.27, which is the same as the pH that we measured, or that we calculated using the ice problem method. So either method is good, but I encourage you to use this method because everybody uses it. You got to get on the bandwagon, you know, and it's a great method. It's just very fast. Okay. So I don't have too much time left, and I know I have this in lab tomorrow, and I kind of wanted to get a little further than this. So I'm just going to address a little bit, what happens when you add acid to the buffer. Let me go to the next page. Well, how about questions? Anybody got a question? I know you have to study this stuff, but if you have a question, you can certainly ask it. All right. Okay, so here's another problem. This is activity 9. I'm going to kind of skip the top part here because I really would like to get a little bit further along. And we've done this type of thing before. So this is really identical type of problem to the one we just did. It's a different concentration of the acid and a different concentration of the conjugate base, but it's the same carbonate bicarbonate system as we used before, okay? So I just want to use the Henderson-Hasselbach equation here to get some practice with that. The H2CO3 concentration from up here is 0.371. The HCO3 minus concentration is, from up here, is 0.350. So pH is pKa. That would be the pKa of carbonic acid plus the log of the A minus over HA. So the pKa, again, is a negative log. Just one thing I want to check. Oh, we didn't do the carbonic before. We did the nitrate, right? Yeah, so no, we did carbonic. 4.3 times 10 to the minus 7. Huh. It's just that I'm using a different value of the Ka here. What? No, I'm not. No. Sorry, I just confused myself. It's cool. This is the negative log of the Ka, which is 4.3 again times 10 to the negative 7. So this is the same as before. This is 6.367 plus the log of, now, this is the A minus and the HA. Okay, and so this comes out to negative 0.0253. Again, this is smaller and this is larger, which is why you end up with a negative here. If it was reversed, then you'd have a positive. And so this comes out to 6.34. So that is the pH of this buffer solution. And like I said, I don't have too much time, but I do want to go over a little bit, and I'll go over this again, on what happens if we add acid to this buffer. Strong acid. Not too much, but a strong acid. So what's going to happen is that the H3O plus or the H plus, whichever way you want to think about it, from the strong acid reacts with the conjugate base of the buffer. Okay. Okay, so in general, if we have a buffer with HA and A minus, okay, the the conjugate base would be A minus. That would react with the H3O plus. This would go all the way forward, giving you HA and H2O. So what this does is, however much H3O plus you had in there, it decreases. It decreases the concentration of the conjugate base, the A minus, and it increases the concentration of the weak acid, HA. So in our case, our acid is the conjugate base is HCO3 minus. It will react with H3O plus. It'll accept a proton because it's a base. It'll form H2CO3 and water. So the concentration of H2CO3 increases, and the concentration of HCO3 minus decreases. How much? Well, it depends on how much H3O plus you had in the solution. So to put some, numbers on this, if you add 1 milliliter of 6 molar HCl, add 1 milliliter of 6 molar HCl to 200 milliliters of the buffer. That's what's going to happen. So we want to know, how is the pH going to change? So the first thing you have to do is solve a dilution problem, because you're adding strong acid to this liquid, to this solution. And now right after you add it, you have a certain concentration of that strong acid, and you need to figure out what that is. So you will do an MDVD is MCVC problem, and you'll get your MD. So just like before, we'll say, okay, we have 1 milliliter of 6 molar. So concentrated molarity is 6 molar times 1 milliliter over. Now, we added it to 200 milliliters. We're adding 1 milliliter. So the final volume is 201. That's what we divide by. And this comes out to 0.0299 molar. Well, that's the molarity of HCl right after you added it. But that is really the molarity molar of H3O plus, because all that HCl becomes H3O plus. So I don't have time to exactly do this with you, but what happens is that H3O plus reacts with the bicarbonate, the base part of the buffer, forming the acid part of the buffer. So what happens is the concentration of HCO3 minus decreases. What was it before? It was 0.350. So it was 0.350. Now you have to subtract the amount that reacts with the H3O plus, which is the amount of H3O plus that was added. So this is going to be its new concentration, 0.320. At the same time, the concentration of H2CO3 is going up. It was 0.371, but now it's 0.371 plus 0.0299, which is 0.401 molar. So this is the new concentration of H2CO3. But what we do is we use the same equation. pH is pKa plus the log. And now we simply adjust and put in these new amounts. You'd put this in here. And then the other one for the acid, we'd put down here. So that's going to adjust the pH a little bit. And when you put these numbers in, just to finish this, and the pKa is the same as we had before, this turns out to be minus 0.0980. And so here's the big conclusion. This is the pH. Do you remember what the pH was of the buffer before we added the acid? Before adding acid, it was wasn't that different. It was 6.34, I think. Yep. So this pH went from 6.34 to 6.27. That's not a big change. Next time I'll show you what happens when if you had just added that to water, the pH would have changed drastically. So I know I'm going to go over some more of this next time. And those of you who have a lab tomorrow, I'll have to go over some of this in lab, but that's okay. I think that's really that was a lot for one day. Sorry about that. Just the way it worked out. But anyway, that's it for buffers for today. Next time we'll pick it up from there. We have one more day to finish up the acids unit, and that's next class. And then we'll move on to, well, then we have a day off, right? Then there's Monday next week and Tuesday next week. There's no class, so we don't have lab on Thursday next week either. So we have our buffers lab this week. Then next week we only have class on Wednesday, and the following week we have our last lab, and then we finish up. So it's getting to the end. So just keep chipping away at it. Okay, it'll be okay. I'll see you next time.
Thank you.
Thank you. Erica, thank you for showing your video. Yeah, you all have a great day too.